Okay, let's start, otherwise we won't finish. Actually, we won't finish already, but that's fine. No, don't feel bad. Don't feel. That's actually a heavy lecture, and but I think it's important. So let's see. So we saw last lecture the ID algorithm or identify algorithm. That's the whole pipeline, right? So we start with a causal. We have a query, but we have a causal diagram. And today I'm going to change to this pipeline. So instead of having in two here a causal diagram, we have a peg. So you see that kind of everything is the same, but the fact that we relaxed the input two is really I mean, I don't want to say breakthrough, but it what actually enabled us to do a completely data-driven causal inference approach, because we can learn this. So this is fully learned from data only, right? A causal diagram, you cannot learn a causal diagram. It's just up to equivalence class that you can learn from data. And here, since the query is just your question, the data is what you observed, and the peg is what you learn from data, you can do everything here without any knowledge, without any prior knowledge. So that's actually very good. And we will see this algorithm, and this algorithm is called IDP, which is basically ID algorithm for pegs. It has kind of a similar structure, if you remember. So in the beginning here, we just do this simplification of the problem where we compute the ancestors of y in the graph p, v minus x. This is exactly as we did in the ID algorithm, and then we have the d, which is this possible. Oh, there is this difference. Now it's going to be possible ancestors instead of ancestor, but it's very similar. But there is one different thing here, and I'm going to motivate in the next slides the difference. But the point is, when we enter in the identify, so this is before, and we call the identify function, and the identify function is here. As in the identify algorithm, we have a condition which breaks. So here is just a new step, but then we have a condition that breaks the problem down in several steps, and you see that's a recursive algorithm. So here we had the lemma 10 that we computed the probabilities using these fractions, right? So we have here a way to compute the Q of something. In the ID algorithm, we were always able to compute the Q of a C component from the probability, the observational distribution. Here it's something different, so I'm going to explain this part. But then in the end, we are going to break down the problem in several small problems, and then in a recursive way solve it, each part here. So basically there are these steps. First, the reduction to ancestral set, then this graphical condition that is going to it's going to enable us to compute the QT minus B from QT. So it's a way to just simplify some distribution that you already computed from a previous step. And in the end, we do the decomposition into, we break the problem into several small problems, and this is going to be related to something that we call regions. We will see all of this. So we start with this graphical criterion, and just to motivate why we are doing this, so I'm going to explain the graphical condition from a causal diagram. It's just, this is not necessary in the ID algorithm, but this was required, so this extension, so the creation of this graphical criterion was required to develop the IDP method. So basically we are going to identify this Q, V minus X, which if you remember, the Q function is the probability of the variable here, which is V minus X. It's just V here, but it's obvious that's V minus X. Given everything else, and everything else is X, right? You remember this, right? And QV is P. Hope you remember this as well. So let's just show some notation. So we call, we denote Cx the union of all the C components that contain, for every C component for variable x in the set x, and then we get the union. So it's the union of all the C components that contains a variable x in the set x. Okay, and then we have the Q of this component. So it's called QCX. So it's going to be the C factor corresponding to the whole union there, the CX. And then we denote for every other C component, we denote it as CI. So we have several others. Each one is going to be a CI. I is going to be 1, 2, 3. And then, because of the, I think you remember maybe this, the Q's can also be factorized into the C factors, right? So each Q corresponds to a C component. And here is just a way to denote first all the Q's corresponding to this union of the X's, and then the product of all the others. So it's just a way to combine the C's X's together, right? So this comes from the factorization into C components. Then denote this Cx minus X, the C factor of Cx, but removing all the terms related to X. It's kind of, I'm removing the X here, so we remove also the terms related to X. And then the probability of V minus X given do X, which is exactly Q V minus X, is going to be, so since we remove the X's from here, we just replace this part with this part, and the other parts continue here, okay? So from this, it's clear that, so this part, the QCI's, they are all identifiable from QV, right? Because they are C components, and the Q's of C components are always identifiable from the QV. So this we saw in the previous lecture. So this whole equation is identifiable only if this is identifiable. This I know that's identifiable, so the question now is this identifiable? This QCX minus X. So that's what we are going to see, if this QC minus X is identifiable from QCX, right? QCX is also a C component. We know that's identifiable, but we want to know if removing the X is continuous, it is still identifiable. So by definition of C factor, you know that the QCX is this whole expression here. So we have the sum over the Q of the U's corresponding to the CX's, right, to this. Before you saw this without the X, so it's exactly the same, but now we have the X here just because we have now a union of C components for every X. But that's the same thing as we saw before. And note here that if there is a condition that if there is no bidirected path in G connecting X to any of the X's children that are not in X, so that's a condition. I'm telling you this. So imagine that you don't have any bidirected path between a variable X and the children of any X's in this set X. If you have this, which can be explained by this red part here, so the C components of all the X's together, intersection of the children of these X's can only have the X's. So basically, is this clear or not? I can make a...
So the children of X have to be in the union of C, in the CX union.
Sorry?
So the children of X have to be in the C union that contains all the X's.
Yeah, I want that the children of the X's are not confounded with the x's, except if they are already x's. So suppose that I have like if I have like an x1, and this is has a child s1. It could also have a child x2. If I have this, is a problem. If I have this, is not a problem. Right? So I'm telling you, if you are under this condition here, then what's going to happen is like, because I'm going to compute the C components of all the x's, and this is going to include only the x's and things that are not children. So the children of the x's are going to be in different C components. So the point here is that under that condition, we will have this fact that the x's are not going to appear after the conditioning bar in this factorization here. I don't know if you remember this, but maybe it's easier to see directly that the Cx minus x is an ancestral set in this GCX. So when we remove the x's, let's make something like this. So the C component of the x's is going to be ax1 and x2 because they are connected by a bidirected edge. And after removing the x's, the ancestors of these variables that are not in. So basically, I need that Cx minus x is an ancestral set. In other words, I need the ancestors of Cx minus x in this graph over Cx is contained in the Cx minus x. So if I have, by contradiction, if I have this C1 is going to be part of the conditioning set, and then when I remove the x's, I have to compute the ancestors of C1, and then the x's are not part of Cx minus x. So basically, it's not going to be a ancestral set. However, if I have this condition, so if it's holding that all the children are unconfounded, I will never have a case where the ancestor is not part of the set. So because you first cut the Cx, remove the x's, so everything that's ancestor is there. It's always going to be this case. So this ancestral reduction is going to hold always. So the QCx minus x is going to be the sum of QCx. So that's the condition that is always true if the Cx minus x is an ancestral set in the graph over Cx, if you remember this from previous lecture. It's okay if you don't remember it. You're making several faces.
Is it not a problem, or what happens if there's no bidirected edge from A to X2?
Like
then
this?
It's not part of CX, right?
Yes, but then you first cut the graph in the C component.
Oh, right.
So this is no longer there.
And it's not part of the
And then it's not part of there.
So it doesn't matter.
Yes. So it would be a problem if you cut the ancestors, right? And it's part. Anyways, everything here is just for you to believe that this equation holds under this graphical criterion. And maybe you can try at home to make it clear. From the previous slide, you saw this decomposition, right? So the QV minus x is the Q of Cx minus x plus the product over the QCi's. This was in the previous slide, remember? So, and now we have the anyways, this is also it was also in the previous slide. So the QV was also the product of the QCX product of QCI. So this is just the CX, and this is the CX minus X. So that's the So basically I'm factorizing these two Q functions, the QV minus X, which is this product of Q functions, and the QV is this product of Q functions. Okay, the only difference is that QCX minus X is here, and here is QCX. And that's exactly what we are going to see. If this is computable, this is computable, so what's missing is getting this part from this part. But I'm showing this for you because I can kind of have this conclusion. So from the first equation here, I can replace the QCX minus X with this sum because of the ancestral reduction. This is what I'm doing here. And the product keeps the same. And this product, because of the second equation, so we just, we put this in evidence. So this is exactly the fraction between QV and the QCX. So we replace the product of the QCIs by just the fraction between QV and QCX. And this is what I'm doing here. So I replace the product with the fraction. Okay, so this 2 was in the previous slide. I'm just doing some algebraic manipulations and showing that the QV minus X now depends only on the QCX. So, yes, so we now can work on with this expression here. And under that condition, right, under the graphical condition. So now this was stated, I don't know where, but I think the reference is going to appear here. But this was stated, I think, in Jintian 2000, in his thesis. But there is this theorem, I mentioned this in the beginning, that there are some conditions to check non-identifiability. And that's a theorem for, so that's a if and only if condition. So if you don't have this, you have no identifiability, but for joint intervention distributions. And this is a theorem by Jintian, 2002, that says the following. For any set of nodes X that's in V, this expression, the QV minus X, if you remember, is just the probability of V given to X. So it's the joint, so remember, it's just the probability of what's here given the do of all the other variables, and all the other variables is just X. So this expression is exactly probability of V given to X. So this is the joint distribution, the joint interventional distribution. And the identifiability of the joint distribution, which is different than the probability of Y given to X, which is not the joint. But we have this theorem that guarantees identifiability of the joint by only checking this this fact of the children being confounded. So if and only if there is no bidirected path in G connecting X to any of the X children that are not in X. So it's exactly checking if any C component contain the children of the X's. We will see some examples, but that's the expression. That's just saying the same. So you compute the C components of all the X's and check if the intersection with the children is just within the X. Moreover, if the V given to X is identifiable because of this condition, so it's a if and only if condition, it's going to be given by this expression, which was the one that we just saw in the previous slide. So it depends on only Q of CX.
I'm a little bit confused. Right now we're not already looking at pegs, right?
No, I'm just motivating you this condition because this condition is one step of the algorithm. And in the idea algorithm, we don't use any of these conditions. We just directly break them into C components. And this was required, like an extension of this theorem for pegs is required for the IDP algorithm.
And the bidirected path, we have it, but it's not co-founding, it's just a bidirected path.
Bidirected path is a path consisted of only bidirected edges,
Okay.
right? So, and it creates the C component. So, for example, I have a B here. So, if I have this, I have one C component, two C components, and another one here. But if I compute, if I have now this, I have only one C component because it's connected by a bidirected path.
Isn't it the given then that in the C component there is no bidirected path from a child in X to one outside of X because it's the same C component?
No, I'm telling you that this equation here, probability of V given to X, you're going to have an identifiability of this interventional distribution, so this is a set, only if and only if you compute the C components of X, it doesn't include the children of X. So this graph is the ball graph.
Mm-hmm.
The X is confounded with one of his children, with it's just Y. So they are in the same C component. And because of this, the probability of Y given to X is not identifiable, but that's just for the joint, right? And the joint is just Y in this small graph. But if you have like a larger graph, we will have examples. You can detect identifiability of the joint interventional distribution by just applying this graphical criterion. From this part, I think it's just important for you to know that you can identify the joint by just this condition and automatically give you the expression. So that expression we understand already how to derive it. And the continuation, it comes from, so you remember from the previous lecture, we computed the Q of every C component by getting these fractions according to the topological order. And in the end, it was always the conditionals. Remember this? And that's what I'm kind of showing here. So it's the product of the condition of the conditionals of every variable given every variable before. So if you just apply the lemmas in the previous lecture, you get this expression here. So I'm just replacing QCX with the product of the probabilities of every VI within CX. Comes from that lemma. So PV is what we have already, so QV is equal to PV, and everything else is computable through these fractions that I explained to you last lecture. So that's the point. You can identify the joint interventional distribution easily if you have that condition, that graphical condition. Okay. Yeah, now there is a reference. So that's, if you want to see the reference, is the theorem 3 by Jintian in 2002. The theorem in this paper is using X as a singleton. It's just one variable, but it's easy to prove that this also works for sets of X. Yeah, so if you want the completeness, because this is just the if part, if you want the only if part, you have to check the paper. I won't show the proof here. But it's here, page 949. Okay, so this is just a copy just for you to, in case you don't, if you want to check, but now we have examples. So this is a graph over V, and V is X, Y, and Z. If I ask you what's the probability of Y and Z given to X, I'm asking you the joint interventional distribution. So you can apply the theorem to check this identifiability because it's the joint. Okay? So and it's a if and only if condition, so you can check if this effect is identified. So for this first graph, I ask you, probability of Y and Z given to X is identifiable? No. Why?
There's a bidirected path from X to Y and Y to child of X,
Yes.
but not in X, obviously, since it's not.
So you see, it's not the bow graph.
X to Z.
So the
There's
x,
a path
there is
Ah,
a
yeah.
path.
from
So-
X to.
Okay, yes.
Yeah, so you need a path, doesn't need to be a bidirected edge, can just be a path. So that's maybe a more interesting graph than the bow graph. And you automatically know that the effect of both, it's very, very important to remember that's the joint. Sometimes you can you have identifiability of the one variable given to x when you don't have the joint. So, but for the joint, you can apply this theorem, and in this case, we don't have it. What about this one?
Should be fine.
Is identifiable because there is the action is on x, and there is no bidirected path connecting x to his child, which is y. Actually,
And-
z
and
as well.
Z.
Yeah, both are child, but there is no bidirected edge between the x and them. So that's identifiable. What about this? It's kind of similar to the first, but the edge is different.
I mean, y is a child of x, but we have the bidirected graph from x to y over z.
Yeah.
So it's not working.
And this one?
Also
Not identifiable just because, so the child is just z. However, this path here connects x with z in the same c component. Okay?
Does it apply to only children or generally descendants?
not.
Children.
Ah, okay, okay.
Yeah. Here, if it was descendant, it would be automatically because of this edge, but it's not this. I ask you children. And a child is the only z. Z is the only child.
So if the bidirected edge from Z to Y wasn't there, it would be okay.
Yes, that's the front door. I mean,
Yeah.
the front door for the y and x, but yes, but you have also for both. Okay. So that's the graph from our previous lecture, and I ask you if this is identifiable or not.
It's not.
Who said that? You?
I said it.
What's the C component? Okay, what's the bidirected path? Now, first of all, what's the which condition you are checking?
I was checking if there is a path from the V1 to any of the.
It's only the child, not the descendants. It's only the child that matters.
Oh, so from the V3.
No, the only child of
V2.
V1 is
V2.
V2.
Oh,
So,
It's not part of the C component, so it's not a problem.
right. So it's like a path, a bidirected path connecting the variable in the action to any of its children.
Okay.
If it
Since we're always skipping one.
Yeah,
thing.
if this was a set, I would have to check any children of any x, right? Not necessarily only its children. Okay, so this is okay. And the C components in this graph, we saw this, are these two, but I want you to use the condition we just saw. I want to identify Q V minus X. And to identify Q V minus X, I need to break into, I just need the Q CX, right? The C component of X. And the X is V1. So the C component corresponding to my X is the yellow one. So I'm going to break this. Yeah, this is I know already. So I'm going to break the Q. I'm going too fast here. So this we saw before. So this is just the QV. The QV we can break into C components. However, the QV minus V1 which is the PV minus V1 given do V1, is given by this formula, which depends on only Q of CV1, right? We saw this. So the QCV1 is the Q corresponding to the yellow part. So when we so from this line here, we have the QV is everything here, and the QCV1 is QV divided by QC1. We can just QCV1 is equal to QV divided by QC1. So basically, I can get this fraction here is exactly QC1, which is the green. So it's here. Are you following? And the sum over V1 of the QCV1, which is this one in yellow. So the fraction QV divided by QCV1 is QC1. So here is a fraction. So that's QC1. And here is sum over V1 of QCV1. And QCV1 is this one.
Is there a reason why there's a capital V1 in the line above and then there's a lowercase v1? I mean, because it looks like lowercase means that the small v1 is getting removed, but wouldn't that make it a different set technically then?
No, here probably is a mistake. So here you usually use small letters for the values of the variables, and this is representing the instantiation of the probability. However, when I moved here, it should be this V, so it's a mistake. Maybe because I put the sum here with the small value. I was using like a sum over all possible values of V1, and but here this V1, it's this V1 because it's the C component of V1. So this V1 is the small, and this is the large one. Here is also the large one. Yeah, sorry. Anyways, but here we kind of computed the probability of everything else given do V1, which is this, using that expression we saw. So that's an expression for the joint intervention and distribution. It can give that's the whole thing. So that's identifiability because nothing here depends on do. So we already have the expression. Okay, it's too much, I know, but it's fine up to here. Okay. It turns out that we can change the V to any set T. So going back here, you see I changed V to T in the title, right? Because it doesn't matter if it's the whole set or any set that contains X. And that's in this paper in 2018 by Jaber. And actually it's Jaber, but anyways. The theorem is just an extension of Jean-Tien's theorem for the joint intervention and distributions, but it's just showing that works for any subset of V. So you can check later, it's exactly the same. The only difference is that instead of having V, it's the T in V. And instead of computing key V minus X, we can compute the probability of T given to X. And instead of knowing QV, which is the observational probability of the entire data set, I have just a subset of it. But I know I have to, it's identifiable from QT. And this is going to be important because we are going to break down the problem by knowing some probability, some joint probability distributions and trying to compute the Q factors from it in the ID algorithm. So the QT is it's always identifiable, right? And now the QT minus X is going to be identifiable from QT using the same condition, but now in the graph GT. You need to remove everything that's not in T, so you get the graph only over T. and then apply the condition of the children in the graph GT. Okay? So in GT, you check the C components of X and the children of X. And if the intersection is contained on X, then you have the condition, and this QT minus X is identifiable. Moreover, the expression is the same. So here we showed that the probability of V given to X was this, but in the numerator was QV. Now it's QT. It's the only difference. And it's the same expansion using these probabilities. It's the conditionals of all variables given all the others that come before. But now, since we are under this QT instead of QV, and this represents an intervention on do V minus T, so in everything else that's not in T, all the distributions that are here are the probabilities under do V minus T. So basically we had before, we assumed that we have the observational distribution, the PUV. Now we assume that we have T, probability of T, given do V minus T, which is QT. So just assume that you have it. And this is a probability, so that is a weird notation for it, but it's a probability distribution. You have an expression for it. It's identifiable. So now it's the same thing, so it's represented by QT, but every time that you apply the factorization, you need to use this probability under do T, V minus T. Okay? It's just a weird notation, but it's the same expression as before. Yeah, so this we know already. Okay, and remember that it's under the do V minus T. So before we had this product without the do's, but now the product of QC X is in the graph GT. So you just converted the G to GT and the PV to P of T given to V minus T. Okay. We will have some examples, so don't worry about it. All right. And then with this graphical condition, it's possible to reformulate the ID algorithm, the ID for causal diagrams. So this is just an equivalent version of the ID algorithm. So you have here first the reduction of the ancestral set, then you compute the C components in this graph GD, and you call the identify function of every C component in the graph GD, knowing what's the corresponding C component. This is computed inside, but this is going to try to identify the QDI given the corresponding C component in the graph G over V, the entire GV. And the difference here is that we have the condition here. So before I told you that this is not required, but you can actually break the conditions in the original algorithm by using this condition that we have a variable B. And this is just one variable. So we are breaking into variable by variable and computing Q T minus B if the condition applies, if the graphical condition applies. And so basically, in the end, so that's just a corollary because we are, instead of using the set X, we are using here just one variable B. So our B is the I forgot what letter I was using, but I think it was X. So we were breaking the problem into sets. Here we can break it just into variables. The only problem is that this is more convoluted. Instead of breaking into C components and going directly to the answer, we are breaking into variable by variable, and this is terrible. So that's why the ID algorithm is not like this. However, and that this atomic criterion is not necessary. However, for PEGs is required. You see why, but that reformulation was required, and you see now that that works. So we are going to next see the extension to pegs of the graphical criteria. Questions up to here? Okay, so let's generalize the same thing. So how can I compute the joint? So this is the Q of t minus x, which is this expression from Qt, right? So that's what the Qt means. But now from a peg. Why pegs are complicated? Because of the circles. Circles, they mean uncertainty. Like it could be either an ancestral relationship or a non-ancestral relationship. So we call these components as buckets. So let's define buckets here. Bucket is just a closure of nodes. So it's just a set of nodes that are all connected with circle paths. So just variables that are connected by circle edges. So in this example, which variables are connected by circle here? So you get, for example, A has W connected by a circle edge, and also Z connected to a circle edge. So these three variables form a bucket. Now this X doesn't have a bucket because there's no variable connected to it by a circle edge, and Y is alone in a bucket as well because there's no other variable connected to it using just a circle edge, right? So the list of buckets are A, W, Z, then X alone and Y alone. So it's just sets of variables that are connected by a circle edge. Okay. What about this one?
Only x1 and w.
Right. So that's the list of buckets. We have x1 and w together, but the others are all alone. In some papers, people, instead of calling this as bucket, they call it a circle component. It's just for you to know. And topological order in a peg, it's a bit tricky, but it's kind of intuitive because the point is like we don't know what happens in a bucket. So we don't know if, for example, W comes before A or A comes before W. So that's why the topological order is over buckets. So to construct the topological order, we have actually an algorithm, but the algorithm is just to make it easy. It's basically intuitive. So let's just read here. So first, create single-toe buckets containing every variable. I think I have here. So everyone is in a bucket alone. Then we are going to merge buckets if there is a circle edge between them. So in the case here, we have A, W, and Z connected, and the others we don't have it. So we form the buckets. Then while set of buckets B is not empty, extract BI with only arrowheads incident on it. And remove edges between BI and other buckets. So let's
So you start with Y since it's a singleton bucket, but it's the only one that only has incident edges.
Right, so yeah, exactly. So that's a while, sorry. So we get all buckets that have only arrowheads into it. So this is the only bucket that has only arrowheads into it. Like X has this tail here, and the others, I mean. So we extracted from the list of buckets this one that has only arrowheads into it. Now remove edges between BI and the other buckets. So we would, I don't know if I have an animation, I have here. So we remove the edges that are connecting this bucket to the others. So now we have this graph. And we apply again the procedure. So we extract a bucket that has only arrowheads incident on it, which now is X. Then removing the edges between X and the others, we have now this graph. And basically that's it. So we don't have variables to remove anymore. and that's the list of buckets. And it's already in the order of the partial order that we wanted. So first, so it's in the reverse order, sorry. So that's the last one, that's the second to the last, and the third to the last. So basically we just reverse everything. That's the first, then that comes before X, and then that comes before Y. But it's kind of intuitive. You don't need actually to run. If you want to run for larger graphs, you can run it. But basically, you just need to remember that circles are uncertainty. And of course, you can automatically get the topological order by following the impossibilities, right? So Y definitely is the last, and we can have X and then the bucket. With larger graphs, it's more complicated.
What do you do in case of ties? So say there's another, I don't know, Y1 or Y3 that is maybe a direct child of X.
It's the same as in the causal diagram. You have different topological orders. So you don't have a unique. So all of them would be correct. Yes. Okay. So now we know the topological order in PEGs, and we need some other definitions, and this is the PC and the C components. A PC component is just a possible C component. So now, since everything has an uncertainty because of the circles, we need to redefine basically the concepts, but they are all intuitive. So a possible C component, or PC component for short, is just a path between two nodes such that all no endpoint nodes along the path are colliders, and none of the directed edges, which could be either the first and the last, are visible. Because you need to form a C component, right? And to form a C component, so a C component is a fully bidirected path, right? It has only bidirected edges. And in the middle, you are certain that they are all colliders. So we have the first condition. And in the second condition is about the first and the last edge. And the only thing that we can get is a possible, is like a possibility of being this bidirected edge. So either is a directed edge that's not visible, or is already a circle, or is already a bidirected edge. And all of them are possible C components, right? So the important part is that all in the middle are colliders, and if we have a directed edge, which could be in the first and the last, they have to be invisible, right? A definite C component, or this C component, is the one that has bidirected edge, even in the first and in the last edge. Don't know, probably I'm asking here.
Probably V1 and V4 or something?
Yes, I think I'm asking, yeah, sorry. Yes, so I'm asking what is this path between V1 and V4? Is a C component, PC component, DC component? I'm already put the visibility here, but the edge that is in red is the path that's in red is a path that has all variables being a collider, right? And the first and the last edge have circles on it. So it's a PC component. So V1 and V4 are in the same PC component, but this is not a definite C component, right? I should make a question here, but let's just go together. So V2 and V6, so that is this path, right, in red. And I'm asking if they are in the same PC component or the C component, and because of the arrowhead in the first and in the second, in the last variable, this is a definite C component.
And if it's DC, it also automatically implies PC.
Yeah, yeah. V1 and V4 are not in the same PC or the C component when I remove the variable V5 from the graph. So if I remove this variable here, then V1 and V4 they are going to be connected just by this path and this path, and none of them are bidirected paths, right, in the middle. So they are not in any either PC or the C component. So what's the idea of this concept is that so it doesn't matter if we are in a subgraph or in the complete graph, but if I have the information that X and Y are in the same C component in a causal diagram, then definitely they are going to be in a PC component in a PEG, right? So if X and Y are in the same C component in the graph, then X and Y are in the same PC, and why DC? So no, if it's in the DC component in a PEG, it's because all the causal diagrams have this, the variables are in a C component in every graph in the class, because this is an invariance. But the other way around, I don't know why it was written, I have to check this, but having the information in the graph, it's weaker than getting in the PEG. But the fact that if there is a C component in any graph of the class, then it's going to appear as at least a PC component in the graph, in the PEG. Sorry, I think that's in the other way around. So now we can show the identification of Qt minus X in the PEG. I think I can finish at least this part here. So Qt minus X is, so now from a PEG, right? So identifiability of the joint interventional distribution in a PEG. So given a set of buckets T in a PEG P over V, for any bucket, so X is a bucket, T is a set, so we just define any set T, and the Qt minus X is identifiable from Qt if and only if no node on the bucket. So first observation here before I continue is that the do has to be on a bucket. It cannot be on a variable that's not on a bucket, because you cannot identify if you have like a circle component, like several variables connected by circle edges. You cannot identify any of them if they are not together. Basically, because you don't know if this component is confounded, basically. It could be confounded, and then just that edge is never identifiable. But the bucket can be, the bucket together. So the X is always a bucket. So that's the first observation. And then the joint of an intervention, the joint distribution under an intervention on a bucket is identifiable if and only if no node X in this bucket is in the same PC component. Now we are in this PEG where only over T, and no node on X is connected in the same PC component with any of the X's possible children. If we put this in mathematical language, the difference here is going to be just the possible children. So from the causal diagram version, this here was a causal diagram over T, now is a PEG over T, and the condition is the same, but now instead of just children, we consider possible children. And, okay.
Yeah, so if we go to that example there on the board, how would we rephrase that?
We don't have here PEG. Let's see if I have an example. It's too far the example, but okay, here. So So if I have x as x1 and w, so this is a bucket, and I want the q of t minus x. I think that's exactly the question. Consider available PV, so we have PV, and we consider the bucket x, x1, and w in the graph PV. So assuming that t is equal to v, just to make it simple. And we want here that q, we want to identify pt given do x. T is equal to v, and our x is this bucket. Then we need to check if the c components of the axis. Did I define the c components of a bucket? I think you asked too.
Okay, yeah.
Yeah, but anyways, we have to define what's a c components of the buckets. Basically, it's just the union of all the c components for every variable. So we have here the c component of x1, you'll be you'll be there because that's a PC component. This is also part of the same PC component. X2 is also part of the PC component. So this all together is the CX, which is the union of all PC components of the variables in the bucket, right? And then the possible descendants of X include, sorry. Yeah, I skipped here. We went too fast, but that is here. I was here explaining about the children, possible children, and then I would simplify to use descendants. And in the example, I was calling descendants, and it works also with descendants. That's something that I'm going to explain. We should come back, but if we use the condition for children, then the children of X's are W, because it's possible children. So that is like this W as possible child of X1, and X1 and W as possible children of X2.
Wait, but isn't X2 not X? Because the bucket is only X1 and W. X2 is...
Yes, yes, sorry.
Okay.
Yes, so we should consider the possible descendants of the bucket, possible children of the bucket, and this is just the children of X, which is just W, and the children of W.
X1 or Z, and Z. Well, it could possibly be X1, but it is definitely Z.
Yes, and our T is V, so we consider the whole graph. Otherwise, we should have to to compute the subgraph. But then you compute if the intersection is just X. So in this case here, so just ignore the Y because it's a descendant, but the intersection would be X1 and W, and X1 and W is part of X. But let's go back and finish in this example, otherwise it's going to be confusing. So yeah, so basically we have now the I promised that
Yep, slide 17, I think.
it's here. Yes, so rephrasing the theorem into in terms of pegs is going to be exactly like this. So the condition here is if every node in the bucket X is if and only if no node, so I cannot have a node in the set X that's in the same PC component in the graph PT, so in the peg, in the induced peg over just the variables T, with any of X's possible children that are not in X. Right, so we compute the C components, the PC components of all variables in the set X, in the bucket X, and then we check if the children that are not X are part of it. And if it is, it's a problem. If there is not, then we are under the condition here. And if this is holding, if the condition is holding, then the joint of the joint distribution under an intervention on a bucket is going to be given by this by the following expression. We know this already. So QCX is just the Q factor, the C factor over the union of the DC components. Yeah, so this is something that's going to be changed later. So if you consider here children, and here is going to be DC components, and then we can use a similar expression as before. So the probability of T given to X is going to be the probability that you know already. So this is QT. And the denominator is the same. It's just QCX and sum over X of QCX. So this expression appeared before, it's exactly the same, and we don't change here. The only difference is that they have different interpretations in the PEG. So CX is the union of the DC components, and yeah, that's it. And B, so basically CX is going to be a set of all, so if you have several X's, then you can compute this as being, before this was variables. And the only difference is that you cannot consider a variable alone. So the unit in our expression is always going to be a bucket. So you just have the probabilities now over buckets. So BI are over all buckets inside of set CX. But as I said, you don't need to pay a lot of attention on this theorem, because basically it would be intractable if we do in this way. And then we simplify this as we are going to show now. So because of this, we would have like a very convoluted large expression. So we simplified. And basically, the difference now in this proposition is that we have, instead of children, we have descendants. So that's the difference. So the condition is still in the PEG over T, but we evaluate the CX as being PC components, not DC components. And the children now is descendants. Because of this, now you have like larger expressions, and then in the end, we don't have like a very large expression in the end. So in the end, we have this expression here. So QT minus X is just, so you see there's no sum. It's much simpler now. It's in the numerator is just the probability that you know already. And in the denominator is the conditional of X given T minus possible descendants under this intervention that you know already. And yeah, so you see that the buckets are always the units in our expression. We always condition on the X is always buckets. Yeah, so basically under this simplification, although this is not sufficient to identify one component, this is actually sufficient to get a complete version of the algorithm later. Let me just go back to the example, and I promise that we finished here. But that's the final proposition. So that's what we need to know up to now. Basically, the graphical condition is that the joint distribution of the joint interventional distribution QT minus X, which is the probability of T given to X, it's identifiable from QT if and only if the C components in the graph of in this PEG over T, if the C components formed by the union of the PC components of every X doesn't intersect the possible descendants of X, removing the X's. Okay, so let's go a little bit just slowly in this graph. So if my T is the V, I don't have to do anything else, but if it was different, I would have to compute the PEG just over the variables on T. If maybe at home you check the next slides, we have examples for this. But I'll go back to next lecture. Then we know already PV. So this is given. So we know PV and we know QV, right? The next step is to consider a bucket. So in this case, let's consider the bucket X equals to X1W. And in the graph P over T, which is just PV, which is this graph here, we have that the C component, so we have to compute the PC components of every variable on X and then get the union. So the X is X1 and W. And the PC component of X1 are all those that are, so every variable that's connected by a bidirected path, and the first and last edge could be just a possible bidirected edge. So the X1 is connected to A with this path that could be a bidirected edge, is also connected to W, and is also connected to X2. And the other variable, which is W, is the same, because this is visible, so you cannot go to this right side, but going back, it's together in the same PC component with X1, A, and X2. So the C component, or the union, so the CX, so the union of all PC components of the bucket includes X1, W, A, and X2. Then we compute in the graph PT, so T is V, and we compute the possible descendants of all variables in the bucket. They include the possible descendants of X1, which will be W, Z, and Y. And we compute the possible descendants of W, which is Z and Y. And in total, they are the X1, W, Z, and Y.
Do we have the same criterion where the node itself is also a possible descendant?
Yes,
So
here.
that's the same thing.
Yes, but it's important that in the end the intersection is going to have just the X, so it doesn't matter much. But yes, this includes the X. So we check the condition, and the condition is true, like this CX, this set, intersection with this set is just X1 and W, and this is a subset of X, is exactly X. So the condition holds, which means we can use the expression. And the expression is that this one, right? And on the top, T is equal to V. So is probability of V given, do everything that's not in V, which is nothing. So it's the observational distribution. So in the numerator is just PV. And in the denominator, we have X before the conditioning bar, which is the bucket. So we have X1 and W. After the conditioning bar, we have the possible descendants of X. Sorry, we have T minus the possible descendants of X, and T, which is V, minus these four variables here, is just A and X2. So that's the conditional probability in the numerator. And we can kind of simplify this. We have PV, we just open up here. So I got the join and divided into two factors, just to simplify. And on the top. And here you can see that these two factors, they can cancel. So this is the joint divided by the probability of A and X2. So you simplify by cutting the joint, and in the end this go up, and then we have this. So anyways, this simplification steps is not done in the algorithm, of course, but if you want to do by hand, it's always good to apply the simplifications, because otherwise in the end you're going to have like very long expressions. But you computed here the QT minus X just given, just applying the condition. I kind of put simplifying even more. This is also not done by the algorithm, but you can apply some condition independence and simplify even more.
In this case, I mean, we removed all the, I guess, nasty do terms just because T is equal to V, right?
Right, this is easy.
Okay.
if you go here, it's a bit harder. Then, yeah, so I knew already that the lecture is longer than it should, and we kind of started late. But I will continue. So last time, we started seeing the algorithm. So this is the identification algorithm when you have a peg as the input. You have a peg and the observational distribution as input. And it's divided in 3 parts. So the first part is equivalent to the ID algorithm, but uses these possible ancestors instead of just the ancestors of Y. So uses the idea of reducing the set to an ancestral set first. So it's like a pre-processing. And the identify function. So first you just do this type of pre-processing, and then you call the identify function. And the identify function is going to try to compute the QC given that you have QT available, right? So this is, you want the effect of C the effect of every other variable on C, so that's QC, given that you know the distribution QT, that could be either the observational distribution when it starts T equals to V, or when you recursively apply this identify function, you have this QT as an interventional distribution. So you are breaking down the problems into several small problems, and this is going to compute always QC given QT. And the first step of this function is to compute QT minus B, where B is a bucket. So if that is this condition that we talked last time, if this condition can be satisfied, we can use that is a formula. So every time that this condition is satisfied, we can compute this distribution, which is a QT minus B, directly from QT without doing any other, without recursively calling the identify function again. So we call it by just again using C here, and we have what's the QT minus B. We can compute it, so we just call the function by using the QT minus B. That's the thing that you could identify. And if you don't have anything to, if you cannot satisfy this condition for any bucket, then we will be here in the line 9. That is another condition, and this is a condition that we are going to see today, where we are going to decompose the problem into different in small problems, and actually it's going to be in 3 problems. So you can see identify function being called 3 times here, 2 in the numerator and the other in the denominator. So basically we are going to break down the problem into regions. We are going to see here what's the definition of regions, and then we call the identify function for these regions. Everyone here remembers how can you compute this? I stopped here. So we saw the graphical criterion first for causal diagrams, then that's the final theorem for diagrams, right? So for causal diagrams. So if that is this condition where all, if you get the C components of you merge, right? It's the union of all the C components for every variable in the set X, and this C components doesn't include any variable that's a child of X except the axis itself, then this is satisfied, and the probability of V given to X, which is the joint distribution, or this is equivalent to call Q V minus X, right? So this can be computed by just using this weird formula, but this formula is just using PV, which is something that you have, and some conditional probabilities that are derived from PV using the lemma 10 from the ID algorithm. So it's computable. So every time that this condition is satisfied, you can compute the joint interventional distribution of this V minus x, where x can be any set x, and we can do this. And then I showed you that, so those are just some examples, but then I showed you that the ID algorithm, so this is just replacing v with t, right? So this is general. We don't need to be x being a subset of v directly, can be just a subset of t, as long as you have qt available, which is something that we are going to need in the recursive calls of the ID algorithm. And in the end, I told you that we can have this version of the ID algorithm by using the condition. So the condition is here. This is equivalent to ID algorithm that you saw before, but instead of so in the ID algorithm we were using the C components directly, and here we can do we can break the problem into variable by variable. So B here is just a variable that satisfies this condition. So you always can compute qt minus b when b satisfies this condition. Of course, this is not efficient. That's why that's not the main version of the ID algorithm. But this was used as a base for the generalization to pegs, right? So this is what we saw. And then I showed you this also in the previous lecture. How can you compute the same qt minus x, which is the joint interventional distribution from qt, but instead of using a causal diagram, we have a peg. We have a similar conditions. We have a similar statement, but depends on this definition of bucket. So bucket is just this closure of circle. It's like a set of variables that are connected by circles, right? So we saw these buckets. Then we also saw topological order over buckets, which can be done through this algorithm here. Then we defined what are the possible C components and also the definite C components. Basically, it's just the possible C components is just a C component where the first and the last edge they is like this red path here. We don't really know what is the first and the last edge, but it could possibly be a C component where every edge is a bidirected edge, right? The definite C components is when you actually have the arrowheads pointing into the first and the last one. So like, for example, V2 to V6 is a definite C component between V2 and V6. Then we moved to so that's actually is the generalization of the same theorem that we saw for causal diagrams, where the condition is in terms of children, but it's rephrased to possible children here. However, in the end, I told you that we don't really use this theorem. We actually try to simplify it by using descendants instead of children. So that actually is the theorem that we should understand. So basically, to compute qt minus x, which is the probability of t given to x, from qt, we need to just check if x satisfies this condition, right? So if we get all the all the PC components, so now we are in a peg, so we compute the PC components of x and see if, and then we just check if the possible descendants of x are only the x's, right? So all the possible descendants of x which are in the C components of x can be only the x's.
I have one question. I think like 2 slides before we didn't have possible descendants but possible children. So
right, so this is what I said. So this is true, the possible children. So this is a valid, the theorem is correct, but there are two differences here. One is that it's in terms of possible children, and the other is that the CX is the definite C components, is the DC components. So this gives you this equation for the probability of t minus given to x. Okay, so you see that this is huge. It's a fraction, it's a sum, a product, is huge. And this is correct, but I don't want to deal with this monster. Then we derived, so that's, you see, it's intractable in the sense of estimation. It would become like a very long and convoluted, that's what's written here. It would be like a convoluted and large expression. So an equivalent theorem, which is called proposition, it's the same as before. It's now in terms of descendants. So instead of children, we have possible descendants. And instead of DC components, we have PC components. So both of them are correct. And in terms of an algorithm, instead of using the theorem, if I use the proposition, I get the same answers, and the algorithm is still correct in the sense of being sound and complete. So I get completeness using this simpler version of the theorem. So in the end, here, if you see, this is the equation. It's not a monster anymore. It's just one fraction. In the numerator is the QT, is the thing that you know already, right? And in the denominator is just a conditional distribution. So it's the same distribution. So if you see here, both has the do v minus t, because the do v minus t is the part that you know. So you know what's the interventional distribution given do v minus t. This is given. You have it as the input of the algorithm in a recursive way. So it was computed before. And using this distribution, which is no longer is observational distribution, it's a rather interventional distribution, you just need to get the joint in the denominator and a conditional in the denominator. And the conditional one is that you get x conditional on t minus possible descendants of x. So this part of the do v minus t is just an indicator that's the distribution of qt, right? So don't forget, if t here was v, then in the numerator would be pv, right? Is this just the observational distribution, because v minus v you be amped, so that's just the observational distribution, and you don't have here again, so this is amped. So it's just a joint in the numerator and a conditional in the denominator. So it's easy to compute in comparison to that monster. So that's why we rephrased the theorem into this proposition, and that's what is usually used in the algorithm. One important note here that the x has to be a bucket. So you cannot get the x being just one element, one node that has circle. If it's part of a circle component, you need to get all of them together. You are never able to identify an interventional distribution in a node that has just circle on it. You need to get the entire bucket, because it's like you don't have information of this bucket. So you need to deal this as a unit. So our unit here is the bucket. So you can compute this. So so this is what I said, that in the end we use this proposition, and there's no loss of information in terms of algorithm. And then we saw this example. Let's just go over again. So imagine that the t is equals to v, just to make it easy. Then the qv is the pv. And if I say that the bucket is x1w, what we need to compute is the c component of this x, and this x includes two variables, so we need to get the union of the possible c components of x1 and the possible c component of w. So if we go to x1 here, who is part of the possible c component of x? So A is part of it, because it's connected by a path that could be a bidirected path. This is again part of W is part of the C component, the PC component of x1, and x2 is also part of the C component of x1. Z cannot be because this is visible, you know, so Y also cannot be because this is not, so basically every variable in the middle has to be a collider except the last, and here is not a collider. So the only variables are x1, w, a, and x2, and the other part that I need to compute to see if this condition is being satisfied are the possible descendants of x. So the possible descendants of x includes the possible descendants of x1, which is w, z, and y, and the possible descendants of w, which is z and y. So those are the possible descendants of x1 and w. And if we compute the intersection of these two sets, you see that's just x1 and w, which is just x. So the condition is satisfied. The intersection is just contained on the x. So since the condition is satisfied, we can use the formula. So the formula is just the joint in the numerator, and that the conditional on the denominator is the probability of the x. Our x is x1 and w, and it's conditional on t. Our t is v, minus the possible descendants of x. So it's everything that's not in this set. So v includes a, and x2 also besides all these four. So that's why it's conditional on a and x2. And basically now it's just some algebraic operations. So the PV is the joint, but then here I'm just open up just to make it easier to simplify. So I'm just conditioning on y and z, and then conditioning on the others, multiply by the others, and dividing by this same denominator. Then if you see this one in the denominator is just the joint divided by the probability of a and x2. So I can cancel the joint in the numerator and the joint in the numerator and just get the probability of a x2 that goes to the numerator. So we have this in the end. So just simplifying stuff. But I started with this expression. Is this clear? I could even consider some condition independences. So this part is not done in the algorithm. The algorithm doesn't go through all the condition dependence to try to simplify the expression at the most. But just because we are doing by hand, it's always good to simplify so you don't have a monster to deal with in the next iterations. But I'm just simplifying here by using this condition independence. So I'm removing x1 and x2 from the expression, from the first conditional. Then I want to, this is kind of already the next iteration of the algorithm, but just imagine that this is another example. And imagine now that the t is v minus x1 and w, right? So it's no longer the entire set v. So it's just a subset of the variables. And this condition, I didn't remind you, but you have to check this condition in the graph P over the subset T. So you need to compute the peg only over the variables in T, which is just removing the edges connected by on these nodes that you are removing. So for example, here I'm removing x1 and w. So you see that there's no, if you go back here, I'm removing x1 and w. So I'm removing all the edges connected to x1 and w. And if you go next, that's the graph. Then in this graph, I need to check the conditions. So what are, okay, now consider available that we have qt, and which is the one that we just saw in the previous slide. So we have here the expression. We have it. This is done now. So it's given. So we want now the bucket x2, And so the choice of the bucket is going to be in the algorithm for any bucket that satisfies the condition. And I'm telling you that this is going to be one. So I'm kind of going through the algorithm, but just consider this that's just one iteration just to apply the proposition. So consider the bucket that's just x2, and I have to evaluate this the condition in the peg over v minus x1w, which is this one. And the C components of x2 is just x2, it's isolated. And the possible descendants, again, is just the same. So the intersection is just x2. So when we apply the expression here, we have this the distribution that we have available in the numerator. I'm using this notation. I think I mentioned this notation before. So instead of using the do in the right side, I can put the variables that are receiving the intervention as a subscript. I think in the end of the lecture, it will be very clear why I'm doing this. Let me just go back here. So I have available the probability of y, z, a, and x2 given do x1 and w. So I'm just using this other type of notation, but that's the expression for it. And this is the same here. So that's the probability of t minus x, which is, I'm writing it here. So t minus x is going to be the our t is this, and our x is x2. So it's this set minus x2, which is just y, z, and a. That's why it's here. And the do is in everything else. So it's x1, x2, and w. In the numerator is just the distribution that I computed. So it's the qt, which is this expression. So if I go here, the numerator is just the same expression. And in the denominator, it's that you need to think now that you need to apply the operations to get the conditional. So I need to get a conditional given a probability distribution. I just get the joint in the numerator, and I need to marginalize the variables that are not conditioning on the denominator. So here I want the probability of x2 given y, z, and a. So in the numerator I have the joint, which is over x2, y, z, and a, and in the denominator I have to condition on the probability of y, z, and a. So I just need to marginalize over x2. Got it? No?
I think I'm a bit confused with how to exactly read that, I guess.
So imagine that you want to compute the probability. Any better? Imagine that I want to compute the probability of x2. That's really bad. x2 given y, z, and a. Y, z, and a. Forget about everything that's here. So how can I do this? So this is the probability of x2, y, z, and a divided by the sum over x2 of probability of x2, y, z, and a. So everything is in terms of the joint, because I have the joint. So I have to put in terms of the joint, so I can replace the joint with the expression that I have there. So that's what I did here. So I have the sum over x2, and in the numerator I have the joint. So now it's just an operation over these things. Is clear now?
My part was more along the subscript notation, I guess, in a way.
So the subscript is just saying that this p is not the same p as before. It's a new probability, which was computed given the do over x1 and w. But there's two ways of writing this. Either I put in terms of do, or I can put here. It's just a notation.
Okay.
It's the same thing. So sometimes we prefer to put here because otherwise it keeps to be very long, and we forget that this is just a distribution. It's another p, it's like p prime. So it's just a way to indicate that's another probability distribution which was computed already. I have an expression, but I don't want you to see that what was happening. Okay. Then, I mean, just simplifications here. So you see that I could, what I did here was, I put the sum here and then I removed the x2. Then I have just the probability of A, and this cancels with this one here, and then this one cancels with the other one here, and then this goes up. Okay, so just simplifications. Okay, so any questions up to here? So now, we stopped here last time. And the last part of the algorithm is to factorize the Q into sub-problems. And I said that this is in terms of regions. So let's see what are regions in pegs. So regions, so given a peg over V, right? Imagine that I have these subsets here, anyways. So A is a subset of C, which is a subset of V. And the region of A is always with respect to this C. It's going to be denoted as something like this. So it's the region of A in the subset C. It's just the union of all the buckets that contains nodes in the PC component of A in the induced subpeg PC. We go by parts here. So let's see an example. So I need the union of all the buckets for every node that's in the PC component of A. So I start by, I'm just listing here the buckets, but I need the PC components of some set. And suppose that the set is the Y1. So the PC component of Y1 in this example is everything. So we started with Y1 here, and you see that X2 is part of the same PC component. This one is part of the same PC component through this bidirected path. Then if I go right, the Y5 is part of the same PC component. I can go further here. So going to X2, then X1, then through this path I go to Y3. Then I can go either right to Y5, 4, or I can go left to Y2. It's not the same PC component, but by putting together, those variables are part of all the PC components of Y1. And if I want to compute the region of Y1, so this example is kind of boring because it's everything already here, but I would have to put the union of the buckets of every node that's here. So I would have the bucket of Y1, the bucket of Y5, and so on. Let's just make it a bit harder so you can see something more interesting. So suppose now that the C is a subset of V, is not everything here. Then the buckets in the PC, in the peg over C, are, so I have the bucket Y4 and Y5 together because they are the circle components. And all other variables are alone. And if I want the PC component of Y1, then it's just Y1 and Y5. However, when I get the region of Y1 in the set C, is together with the y4, because I have to put together all the buckets for every variable in the set. So I get the PC components, and then I get what are the buckets for y1 is just y1. What are the buckets of y5 is this one, so it's y5 and y4. So it's just the union of all the buckets of the variables that are part of the PC component of A, which is my set here. It's just, if you want to think about it, it's like a C component is like a set of variables that's everything is confounded among everything. It's like something that you don't know if there is a bidirected between them, so it's confounded, so you cannot deal with this in causal terms.
I have one question. Probably the answer is very easy. But the PC component of y1, why does it only include y1 and y5? Because there could also be a bidirected graph between y5 and y4.
It couldn't. It's a definite non-collider. This is not connected.
Ah, yes. Okay, yeah.
So in the end, you can trust that this is a valid peg. And if it's like circle, you just ignore it. It's going to be definite non-collider. So to be PC component, every variable in the middle of the path has to be bidirected, like it has to be a collider. And then you just look at the first edge and the last edge. And if I'm looking at this could be a bidirected edge, but then this cannot be.
Let's turn that around.
Yes.
Yeah. Okay, because they are y1 and y4 are conditionally independent.
Right.
Yeah.
For the region of A is just completely arbitrary, right? We can choose whatever we want.
Yes.
Or does it make sense to have A be a bucket, for example?
A and B?
The region of A with respect to C, I guess by definition you would always have the whole bucket of A in that region.
Yeah,
right?
so bucket is always, there's only one bucket. So the bucket's the every variable that's connected by a circle. So
right, what I mean is if you take A as a single element, even though its bucket isn't a single element, the entire bucket would be in A regardless, in the region, sorry.
I understand what you're saying. So you're asking if A is a bucket or not. So in this definition, doesn't need
It
to
doesn't
be,
matter.
but the algorithm is going to be a bucket. Okay, now it's another example. Let's suppose that A now is y2, and the PC component of y2 is here. So now we can include up to y4, right? Because that is this path. The variable in the middle is a collider, and I stop here because this is not a collider. So, and this is okay to be a circle. So y2, y3, and y4 are the variables in the PC component of y2. And the region of y2 in the set C is going to be the union of the buckets of everyone here. So the union of the bucket of y2, which is just y2, the bucket of y3, which is just y3, and the bucket of y4, which is y4 and y5. Okay? So now you know regions. So we can decompose the QC using the following theorem. So in a peg, which is going to be over V, and let's suppose that I have a set C, which is a subset of V. The QC, which is just the probability of C given all the other variables that are not in C, decomposes as this fraction. So is the product of the Q of the region of A, where A is a subset of C, so A can be anything here. Then I get the region of the variables that are in C, but it's not in the region of A, divided by the intersection of these two regions. Let's see an example. So suppose that the C is this as before, so it's just the y's. Then I want the region of y1, so I get A equals to y1. We just saw that the region of y1 is y1, y5, and y4. And the other region is the region of C minus the variables in the region of A. So I get every variable that's in C, but it's not in the region of y1. So it's going to be y2 and y3. So I want the region of y2 and y3 in C. And then I don't know if I computed this already, but I think we computed. So basically we need the C components of y2 and y3 and the buckets of them. So y2 and y3 have the same C component, which is this one. And then we just need the bucket, which is going to include y5. Then the factorization is going to be the Q of region y1. Let's just go back here. So the Q, go forward. So the Q of y is going to be the Q of the region of y1. So it's the Q of y1, 5, and 4, this one. Then the Q of y minus the region of y1, which was this one here. So it's the Q of y2, 3, 4, and 5, divided by the intersection of these two regions, which is 4 and 5, which is here.
Why is y the name of the variable in the qy?
Sorry?
Why is it qy all of a sudden? Why do we stop calling it qc?
Yes, it's because, sorry.
No, I was curious if there was something I was missing.
It's just because the C is all y's, and
okay.
for some reason I don't know, because sometimes I copy this from a paper, I guess I was calling this y as the set of y's, but it should be C. Yes. Yeah, but that's all the y's in the set here. Yeah, good catch. So now we can generalize the ID algorithm to pegs because we have everything. So this is just a copy of the first slide. So we have all the components. So you see that first it has the reduction to the ancestral set. Then in the line 6, we evaluate for every B, and B is a bucket. You see here that the B is a bucket. And we need to evaluate if that is a bucket that we can apply, that satisfies the condition, so we can compute the QT minus B directly without calling any recursion. And then we call we compute the C given the T minus B already. Otherwise, if we don't hit the line 6 for any B, then we have to decompose into 3 problems, right? We factorize the QC into this fraction, which has the regions. Then we call again over and over until if either we return the answer or we fail. And the algorithm is complete. And by the way, the code is available. It's available in my GitHub here, so you can download it and apply. Before going to an example, I want just to clarify what's being identifiable in a peg. Maybe this was, I think it was clear, but just reinforcing the concept. So a peg is a class of modules. So when I say that the effect, for example, in this case, the effect of X on Y is identifiable even through backdoor. So you can get this expression either by applying the backdoor adjustment on a peg or just running the algorithm. But every time that the effect is identifiable, this means that I can construct a causal module that's part of the peg, and the effect is going to be identifiable in the graph using the same formula. So it doesn't matter and you see the formula, it's in terms of the joint distribution. So it doesn't matter what's the graph. So this is another model that's again part of the class represented by the PEG. So these two models, by the way, it's clear that those are part of the same class. So
how is that the zy in the second one bidirectional?
because this edge, first of all, is not visible.
Right.
If it's not visible, means that z is ancestral of y, which means that there is a path from z to y. However, this could be represented by a bidirected edge. So it's sometimes hard to see. So that's why there exists the concept of visibility. So W here makes the edge between x and y visible. So I would never have a bidirected edge between x and y. Although it's always the case that the x is ancestral of y, so you detect that's a cause by checking the edge, but the identifiability depends on the visibility of the edge. For example, here I cannot compute the effect of z on y because of the existence of a model that's confounded. So I would never compute the effect of z on y here. So if you try, for example, backdoor doesn't work because this path here is it's a possible directed path, so I cannot apply the generalized adjustment, so it's not identifiable. However, the effect of x and y is identifiable. So the meaning of the edges in the PEG are just ancestral relationships, and you see that this is a definite non-collider. So here it's a non-collider, here's a non-collider. I would never have bidirected here and here at the same time. So I know that conditioning on z, I would never open a path. So that's why it works. Z is blocking all the confounding paths. Doesn't matter what's the model. So that's the idea of the definite non-collider. But this doesn't mean that this is a direct edge in every model, right? It's an ancestral relationship. So that's the concept of effect identifiability in a PEG, means that the same formula is valid for all models in the class. So doesn't matter, even if I don't have identifiability of the model, of the structure of the model, so I'm working the equivalence class, doesn't matter because the formula is going to be the same. So the effect is identifiable in every model of the class and using the same formula, right? So this is what's written here. What no identifiability means. So in this case, for example, x, the cause of x and y is not identifiable, so I don't even know if it's a cause. So there's a circle here. So it is possible that in some models that are part of the class, the effect is identifiable. But I don't know, from here, I don't have the knowledge to know that that's the true graph. I could have other, like this one, where even x being a cause but could be confounded, but in this case could be just confounded without cause. So I don't know. So first of all, there are some models where the effect is not identifiable, and I don't have a way to just apply the same formula regardless of the model. So that's why it's a non-identifiable effect in the PEG. Okay. Okay, so I have an example here, just going through the algorithm. I hope it's not too much. That's just before we finish this lecture, then we start the other. I'll give a break. So suppose that this is my original PEG, right? So this is the input. So here I have the algorithm. And the first line here, line 1, asks me to compute D as the possible ancestors of Y in the PEG where I removed the X. So so I want to compute the QY. So the QY is the effect of everything else on Y, and everything else is my X. So in this example, I just need to compute QY, and the D are the possible ancestors of Y. The possible ancestor of Y in the graph removing the axis, so I have to remove the axis here and then compute the ancestors of Y, the possible ancestors of Y. So
That's just Y because that's the only thing remaining,
right,
and you're always
yes.
an ancestor of yourself.
Right.
So.
I don't have here the graph removing the axis, but obviously it's just the Y's because the ancestors of every variable includes itself, so I don't even need to look at the graph. We call identify now to compute the QI from QV, which is PV. So we started from the beginning. So C is my Y, so I'm calling here the identify function, where C is Y, right? I want to compute the QC from QV. So T is V. Okay. I will need this T minus C because now I want to check the condition on line 6. That is the condition to see if there is a bucket that satisfies this condition. And to know this condition, it's a B that it's contained in the T minus C. And the T minus C includes x1 and x2. So I need a bucket that's in x1 and x2, which satisfies this one. So x1, neither of them satisfies the condition. We can check why not. So we need that the C component of them in PT, so my PT is V, so it's in the entire graph. If I get the PC component, the possible descendant, so I have, for example, Y1, which is a descendant, and it's part of the C component because of this. So if I get the PC components of X1, includes everything.
Yeah.
And the possible the possible descendants is not contained on B, which is just X1. And if I do the same for X2, I have this descendant Y2, which is part of its PC component. So neither of them satisfies the condition on line 6. So I go to the line 9, where I have to decompose the problem, and I chose here Y1. So I just need to get any bucket B contained on C, and my C is all the Y's. So I need a bucket on the Y, such that the region of B is different of the entire C. And we computed already the region of Y, and we know that's not the complete Y. Actually, it was Y1, Y4, and Y5. So this decomposition we just saw in some slides ago, some other slides, and the condition here is fine, right? So the region of the bucket is not the entire C. If it was, it would fail, and then it means that the effect is not identifiable. But here it's not the case. So I'm going to show one of the Qs, and then the others you do at home if you want. So it's already a lot. So I think I will start with this one. Q Y2, Y3, Y4, Y5. So we call the identify function. So if you see here, we call the identify function for all the 3 regions. And we are in this one. So we call it for this one. And the region is our C, is going to be our C, and the T is going to be the same T, right? So we call the identify function to compute the Q, this Q here, where C are the variables inside, and T is the same T. we're just breaking, and we haven't computed any other Q, so that's what we have for now. So let's try to do this. So what we need is, so we have the C, we have the T, and we have the T minus C. And I will try to compute the condition 6, in the line 6. I want to see if there is any bucket in the T minus C, so it's a bucket in this set, that satisfies the following condition, that the C components of this variable and the possible descendants, the only the intersection is just B. So it's going to work for the Y1, so the bucket Y1. So in this set here, we are checking in the graph over PT, and our T is everything, so it is still in the entire graph. And the Y1, if you will see what are there's no descendants, so there are two conditions, right? So either we have to check the intersection between the possible descendants of this bucket and the C components. Since the possible descendants is empty.
Well, just Y1.
Yes, Y1, sorry, is just Y1. Y1 is going to be itself, which is in B. Yeah, you are correct. I put here none, but it's just Y1. As Y1 has just itself as a possible descendant, then this condition is trivially satisfied. So we get the B1, and we try to compute now the QT minus B from Q, and Q is PV. So that's what we are trying to do here. B is just Y1, and the QT is our QV. And we use this fraction, which is the joint in the denominator, which is just the PV, right? And so it's everything, x1, x2, y1, 2, 3, 4, and 5. And in the denominator is B, and B is y1. And I get the T, which is everything, minus the possible descendants of B, which is minus y1, or it's kind of redundant. I cannot put the y1, of course, and so it's everything here. It's Q. It's the Q of y1 given everything else. What is this? Okay, I can kind of. So this is the joint divided by the probability of x1, x2, y2, and everything here. So I can just cancel out the joint, and this goes up. So that's the simplification. Okay. So we call now. So that's line 8. We call the identify to compute the same C. So the C doesn't change. So it's still y2, 3, 4, and 5. But now instead of QV, we have the QV minus y1. I just computed, so I have it. Okay, so again the same C, but the T is now V minus y1, and if I compute T minus C, it's just x1 and x2. So I'm kind of reducing the T minus C every time that I recursively call the functions. So I have a different graph now. So the PT is not everything now. It's removing the y1, so that's why it's in gray. So our graph is just what's not in gray. And I want to see again if there's any bucket in the set x1 and x2 that satisfies this condition now in this graph where I remove the y1. And I guess you kind of know that it is now because I removed the descendant. So we have the x1. So x2 is still invalid and doesn't satisfy the condition, but now x1 doesn't have a possible descendant in this graph. So it's going to be it's going to satisfy the condition. If I get the only descendant, again it's wrong here, the only descendant is itself, and it's going to be part of the bucket. So we are going to hit line 6, and we need to compute now the qt minus b, where b is the x1. We have already qv minus y1. This was computed in the last slide. And we apply the preposition to again. So it's the joint is this joint here in the denominator, and in the denominator is the conditional of this distribution given t. Our t is v minus 1 minus the descendants of b, which is none. So basically so it's x1 here, which is b, given everything else of this set of variables. And again, by simplifying, I get just the probability x2, y2, y3, y4, and y5. We call again. So this is identification now of the q, the same c, so the c doesn't change. But now, instead of getting the qv minus y1, we have qv minus y1 and x1. Okay, so I'm reducing now. I don't have these two variables, and I want to check again. So this is my c, it's the same. The t is v minus y1 and x1, and the t minus c is x2. If we try again, the bucket x1, great. The bucket which is x2 has y2 as its possible descendant, and the point here is that the y2 is no longer part of its c component. So it's fine. Now we remove the part that was creating the confounding between x2 and y2, so we can compute the qt minus b. So b is x2. We have from the previous slide that this is qv minus y1 x1, so that's our new distribution available. And we applying the preposition to, we have the joint in the denominator, this joint, and in the denominator we just need to condition on the possible descendants. In every variable except the possible descendants. So we remove the y2 from the conditioning part. I'm trying to simplify stuff here. Don't know why, but we can simplify and get something else. Those parts are optional. The algorithm doesn't do this, but I'm kind of removing the y3 from here because it's independent of x2, and then
because it's basically a collider path, and since you take out y2, then it deseparates x2 from the other things, right?
Right. What's your point?
I was just following along with what. So that was basically the argument for why x2 is independent of y3, y4, y5.
Oh right. Yes.
Okay.
But anyways, I simplified some stuff here. It probably is correct. Now we call the identify function with the same c, now with this new probability that we have available, and it's getting to the end. Don't worry. So that's the last part. So we are going to compute the same QC now from this new distribution that we have available, and this is my C, this is the T, right? This is my T, and the T minus C is the empty set now. And because the C and the T are the same, right? The empty set means that they are equal. We are going to hit the line 5, and then this means that we stop calling recursively, so it ends, and that's our, so the qt, which is this one, is going to be this one. So we return the q, and that's it. It's done for that part. We have 3 parts. I won't do it, but you can just do at home. We're going to do similarly. If you do, you get this for the green part. That's the answer. If you call for the, if you do again the process for the blue part, you get this one, and then putting together, you just get the q's, the return part of this, and that's going to be the answer in the end. And that's the expression of the what's the effect of these 2 x's on all these y's. You see, that's a weird expression, but it's computable from the observational distribution. So you couldn't get this from backdoor adjustment or front door adjustment. It's only through the ID algorithm, but it's an algorithm that it's complete. So if the effect is identifiable, you're going to get an expression in that. Yeah.
Only so few steps.
The first question in the exam.
No, don't worry.
3 hours later, okay.
Yeah, so
Falls recursion.
this would end our lecture. Yeah, so 2:30. Yeah, it's kind of, we still have another lecture, but I'll give you a break. So Jan was really nice to you, and he created a new exercise sheet for you, like a review. He just got a few questions that it were not in the exams last time, and it didn't appear in any exercise sheet here, so he decided to put in a new list. So instead of getting 1 list for next week, you can get 2 lists. It's just 1 or 2 exercises more, but I think it was nice. Here we have a few readings if you want to learn more, and I will put on Elias, I will upload, so last time I uploaded the code using the causal effect R package, which implements the ID algorithm. I have an extension of the same examples using the PEG ID. So if you want to try and see the expressions at home, you can run it. Right, so that ends this lecture. Let's just stop here.